And I observe the success here and apply the observational method and continue without the microphone. So it's time to take a look at the uncertainty and the uncertainty quantification. And then we look at, in the guideline here, we see that, well, we have a chapter on this specific issue, how to quantify the uncertainties here. And there's also quite an elaborate chart that you see here. It's too small to read, but you see there, depending on which situation you have different options and things to consider. It's not really time to go through all those details today, but I will present some basic important concepts here and focus on them. So we're back here to the ground model, and we have some ground properties that Stefan presented that we are now interested to quantify the uncertainty in. So what do we need to consider here? And already in the previous session, we talked about, or the other presenters talked about the spatial variability here. And in principle, there are two ways of modeling and dealing with this spatial variability. We have what we can call the explicit modeling of spatial variability, and that essentially means to have a random finite element model where you specifically have different types of, or different properties in different parts of the model. Quite advanced, possible, but you see it's also computationally expensive. So the focus of the code is actually the other option here, the implicit modeling. We call it the single random variable approach. And the idea is that we try to capture what is supposedly more realistic here, but the results from using the implicit modeling here should give approximately the same results. What we see is that for those of you who have read the code a bit, and you see, if you are familiar with Appendix A, you will also see that there is a clear connection there with the characteristic values and how those are assessed. So part of the material from this morning will also be important here. For example, we have the scale of fluctuation. I was very happy to see that it showed up already this morning, that for larger structure you might want to consider an average value, but for very small parts here, or something that's sensitive to some weakness point or weakness zone, you might want to do a local value, and they have your type A and type B structures, and they also show up here in the reliability-based methods. Yeah, so you get these, essentially the two extremes here come again. What we didn't talk so much about this morning is the uncertainty components here. So Julia and Trevor, they talked mostly about the statistical uncertainty, how many tests do you need to do. What I think is quite important to point out is that there are also other types of uncertainty that you might want to address, and with the reliability-based approach you can do it quite explicit. For example, the measurement error, how precise is your measurement tool? Different measurement equipment are different, have different uncertainty, and quite often we like to do this indirect measurements, meaning that you measure something else than what you're actually looking for, meaning that you have some sort of transformation model. You go from, for example, a cone penetration test to an undrained shear strength, and you have to do some transformation, and that transformation also has uncertainty, sometimes quite a lot. But considering all of these, you end up with a random, single random variable. How do you do it? A quite straightforward way is to consider the coefficient of variation here. We saw it also this morning. And to do it formally, statistically here, and this is also actually an equation from Appendix A that shows up there, is to sum up the squared coefficients of variations from the different parts, And here you also account for the spatial variability with this gamma square factor, the variance reduction factor. And you see here you can also, or should also with the reliability-based approach here, consider the this type C method that was discussed this morning. And in the guideline here, it gives a little bit more in-depth information on how to do that. So if you're interested in or want to work with this type C method, you can also get a lot of information, background information from the reliability guideline. Right, and this was what Julia and Trevor discussed this morning, so I will skip that. But you have here essentially the average value and the inferior superior value, the extreme times. So what happens in the guideline later on is that we see that, well, we have some different suggested approaches to establish which probability distribution you are looking at. 4 of them here. You can fit your fit distributions to site-specific data using statistical tools like maximum likelihood or goodness of fit tests. This is the most sort of explicit assessment of the uncertainty from your data. You can also have combine your site-specific data with values from literature guidelines. It's a little bit more simplified. You can use, for example, indicative values then of the coefficient of variations that are usually sometimes a little bit difficult to assess, especially when you have too little data to do good assessments of the coefficients of variations. Sometimes you might want to consider physical constraints and engineering judgments, and this is especially to deal with the tails to avoid unrealistic values in the tails, so you don't have negative undrained shear strengths or something like that. Would be quite unusual in real life. We also have recommendations for how to use Bayesian methods. It is a little bit more advanced, but also more powerful. But for example, if you have data from different types of measurements and you want to weigh them together, there are mathematical frameworks, statistical framework for how to do that using the Bayesian methods. And also Julia this morning talked about how to deal with trends with depth, and that also comes in here with a bit more in-depth discussion.